Hello, my name is Eric Arney, and today I will be presenting on the state design pattern for my presentation for CIS 476. So let's begin. To begin talking about this design pattern, I want to first go over a problem. So let's discuss this problem. So let's say you want to develop an audio player that that has controls that behave differently based on its playback state. So it has a lock state, which is triggered when the lock button is pressed. If the device is playing media, when the state is triggered, it will stop. If the user tries to press the next track or previous track button, the player will return a message stating that it is locked. And then there's the ready state, which is triggered when the play button is pressed while in the lock state. And when the play button is pressed in the state, it will change to the playing state. The next track and previous track button are still locked in this state. So finally, we have the playing state. The audio player plays media in the state. When the next track button is pressed, the program skips to the next audio track in the playlist. And when the previous track button is pressed, the program goes back to the last track in the playlist. And then while in the state, the play button pauses and unpauses the current track. So, yeah, this is a problem, right? Because we have a program that has lots of different behaviors, and it behaves differently based on the current state that it's in, right? And it transitions between these states based on certain triggers. So, this becomes an issue because how do we solve this problem? How do we write the program so that its behavior changes depending on its state? One way we could possibly do this is through a switch statement, right? So we have some variable that holds the player's state, and based on the state that it's in, it executes some code. Similarly, we could implement an if-else statements, a series of if-else statements in a similar fashion to control the player's behavior based on his state, but these implementations are kind of problematic and weak because, as more states are added, the if-else or the switch statement becomes large and cumbersome. So it becomes difficult to maintain in this way, right? Because if some behavioral logic is changed or some new states need to be added, it becomes sort of harder to deal with, and just overall a mess to maintain with these types of implementations. So what are some other ways that we can think about doing this? Which brings us to another solution that would work better, which is the state pattern, and that is the topic of this presentation. So the state pattern is a behavioral design pattern that allows an object to change its behavior when its state changes. The object will seem as though it has changed its class. The state pattern creates new classes for all states of an object, placing all of the behaviors that are unique to each state in their respective classes. This means that the original object won't need to implement all of those different behaviors on its own. It can instead store a reference to one of the state objects that represents its current state and let the state object handle all of the state-specific work, right? So this is a better implementation because it's more modular. If behavioral logic needs to be changed, we don't have to go hunting through a large if-else statement, and instead it's nice and encapsulated by a specific class. So it's more compartmentalized that way, it's more partitioned that way, and it's cleaner that way. So a state pattern would be better for this, a better solution for this kind of problem. So yeah, a state pattern would work well for this problem. It's because state patterns should be used when an object's behavior depends on its state, and it needs to change its behavior at runtime depending on the state. And the state pattern should be used when operations have large conditional statements that depend on the object's state. So, yeah. This is the basic structure of the state pattern. So over here we have the context, what's called the context, and that is the original object that the user interacts with, and it maintains an instance of a concrete state subclass that represents the context's current state. So we have the state, and then we have the concrete state subclasses that are that inherit from the abstract state class. Yeah, the state defines the interface for encapsulating the behavior associated with a specific state of the context, and the concrete state are the subclasses that implement the behaviors associated with a state of the context. So that's the basic structure. And then the participants we covered as we were talking about the structure, the context state and the concrete state classes. So what are the consequences of implementing this design pattern, right? So we kind of talked about it a little bit, but just to put it into more concrete words, we have all behavior associated with a particular state is put into one object. Since all code unique to a specific state exists in a state subclass, new states can be added by defining new subclasses. And since state-specific behavior is added by individual subclasses, the overall design is less compact, as it increases the number of classes. This is a good thing if there are a lot of states, but can become cumbersome to deal with if and probably overkill if there are just a few states that the context transitions between. So let's think about other motivations and known uses, like in the real world. One example would be handling a TCP network connection. And this connection can be in one of three states, which include established, listening, and closed. So if you think about it like that, the behavior of the connection changes depending on what state it's in. So the state design pattern would work there well. So let's move on to my demo application that I will be presenting to show a little bit more of how example of how this design pattern works. So my demo application allows users to interact with Fido, a dog, in one of three ways. The user can ignore, feed, or play tug of war with Fido. And Fido will react differently to each activity depending on the state that he is in. And the different activities may cause Fido to transition to a different state. So I came up with this idea because I was thinking about those, those, I don't know if you are familiar with those toys that used to be popular in the early 2000s called Tamagotchi toys, where kids could like feed this little computer animal and take care of it. So that's what my goal with this demo application was. So let's dig a little bit deeper into the actual design of this application. So we have the context in this case, which is the Fido class, and the Fido class serves as the context in this implementation. As I said, it has a state object and can switch between different states, but all state-specific behavior is handled by the state subclasses. So, as you can see, there's the private instance of the state class, and when Fido is initially constructed, it starts off in the happy state, and it has the ability to change its state by passing in a state object, and then it also has the ability. It also has the ability to get the state with the get state function, so it can access that state. So my demo application also contains the abstract state class that all concrete states inherit from, and then it defines the state-specific methods that will be implemented by the concrete state classes. So we have the tug of war activity. What will happen based on what state. So then we have the feed activity, and then we have the ignore activity, and then we also have this image object, which stores a specific image that is different for each state. So that's the state class. And then we have the concrete state classes, which implement the methods established in the state class and execute state-specific behavior. So based on how the user interacts with Fido, Fido can be either in a happy state, sad state, or hungry state. And here is a screenshot of the happy state class. How Fido reacts to each activity when he's in the happy state is displayed by these functions. So when you play tug of war with Fido when he's happy, it says Fido loved playing tug of war with you, and now he's hungry. So here we call the context class, and we change its state now to the hungry state by calling the hungry state constructor and passing the context class, the Fido instance, the instance of Fido. And then if the user tries to feed Fido while he's happy, it returns a message, the string saying Fido has too much energy to eat right now, and his state does not transition states. But if you ignore Fido while he's happy, it changes Fido's state to sad, and then it returns a string, Fido is sad that you are ignoring him. So we can see how each of these different activities are different based on the state. So then So now let's demonstrate the functionality of these classes. So this demo application was developed using Java FX and an FXML controller. The user can press one of three buttons to interact with Fido: ignore, feed, or tug of war. Fido's state object is access to display Fido's state-specific response to the screen for the user to see. I'll just walk you through the code really quickly. So, we have the handle feed button. When the feed button is pressed, it gets Fido's state, and then it accesses the on feed method, and then it sets the image to the image of its state. So the state-specific image is displayed to the user as well. And same with the ignore button and the tug of war button. So as you can see, the context, the state object is what's actually handling all of the behavior, the specific state object. So let's boot up the application so that I can demonstrate the functionality for you. Give me 1 second. So let's just run the Fido demo here. So here we have Fido, and we can see that he's happy. So what happens when we try to feed him when he's happy? Fido has too much energy to eat right now, so nothing happens. He's still happy. All right, let's see what happens when we ignore Fido. Fido is sad that you are ignoring him, so we can see that his state image has changed. So he's sad now. So what happens when you try to play tug of war when he's sad? He becomes happy again. It says Fido is so thankful that you are playing with him. He's happy now. And then we can play. What happens when you play tug of war with Fido when he's happy? Okay, Fido was in the happy state, but Fido loved playing tug of war with you. All that playing has made him work up an appetite. So now Fido is in the hungry state. So what happens when we try to play tug of war with Fido when he's hungry? Fido doesn't want to play right now. He is hungry. And that's a specific behavior that's defined in the hungry state class, the hungry state concrete class. So let's feed Fido so that he's no longer hungry, and now he's happy again. So we can see how the different states impact how he behaves, how Fido behaves depending on what state that he's in. We can see those different changes to his behavior, and that's why this is an example of the state design pattern. And then I have one more thing to show you. Hold on. Just the this is the my class diagram for my demo application. So we have the abstract state class, and then we have the concrete state classes, the happy state, the hungry state, and the sad state. And the behavior of Fido is affected based on what state the state object is currently in. And then we have the FXML controller class that handles the UI of the application. So yeah, this was my presentation on the state design pattern. We went over the pattern, and then we also discussed my demo application that implemented this design pattern. Thank you very much for listening to my presentation, and these are also my sources for this presentation. I used the textbook that was assigned for this class, pages 340 to 347, and I also used this website to get more information on the state design pattern. So thank you very much.